magnetic field and having a current flowing, then how it is experiencing a force that we have seen by using the Hall effect. The next we will be seeing is how the charge carriers are generated and how recombination takes place basically. Okay, so here if we consider pure silicon, that is a pure semiconductor is there. So in that pure semiconductor, the charge carriers in this case, these charge carriers will be either a hole or an electron. Okay, if uh, extrinsic semiconductor is there, there will be like the charge carriers will be mostly, if it is n type, the charge carriers will be mostly of electron, and if it is p type, the charge carriers will be mostly holes. But in pure semiconductor, both will be considered as equal amounts, and that will be contributing to the conduction if it is thermally agitated. That means if we are applying uh, temperature to this pure semiconductor, then only it will be having the generation of electron hole pair, and then that electron hole pair will be free to move and will help in conduction. Okay, uh, at 0 Kelvin, this pure semiconductor will be working as a insulator simply. So now we need to study the generation and recombination of charge carriers. So in pure semiconductor, what we are going to do is basically we are going to apply the temperature, or the temperature, or we can call it like thermal uh, energy. We are going to provide a thermal energy. So that thermal energy will be like semiconductor is there, on that we are putting a light. So that light will just be working as a thermal energy or thermal agitation provided to this semiconductor, pure semiconductor. So once we are providing this thermal agitation, what will be taking place is here the generation of electron and hole pair will be there. Okay, so once we have applied the thermal energy, the generation of electron hole pair will be there. That electron hole pair generation will be throughout the volume, so it will be generated per unit of volume. So each volume will be generating, and it will be generating per second. That means at each second the electron hole pair will be generated once we have applied the thermal agitation or the thermal energy. Okay, so but while once this is the case of generation. Okay, on the other hand side, whatever electron hole pair has been generated, some of the electron hole pair will be looking like they are disappearing. Okay, so we can note like while other electron hole pair disappears. So this disappearance is because of the recombination of uh, electron hole pairs. So once we have put the thermal agitation to the pure semiconductor, it will be generating electron hole pair. Okay, and whatever electron hole pair has been generated, some of the electrons would be combining with the available vacancy into the crystal, that will be forming an electron hole pair, and it will be forming such that the electron hole pair will be looking like it is disappearing. So this disappearing will be as a result of recombination. Okay, so here in the recombination, basically what is going to be happen is the free electrons will be falling into into empty covalent bonds. So if the crystal is there, if there is an availability, that means into the valence band, or we can say like in the uh, valence electron is having a vacancy, then that vacancy will be like a hole, so that hole will be occupied by this electron, so electron hole pair recombination will be taking place. So uh, on one side a generation is taking place, and on other side recombination is taking place. So how uh, this basically affects the semiconductor material that we are considering. So suppose we are having n type semiconductor, we are having n type semiconductor. So here at starting, suppose p naught is the concentration, and at t dash time we are turning the light on. Okay, that means we are providing the thermal energy. So once we are providing thermal energy, there will be an increase in electron and hole pair. That means generation of electron hole pair is going to take place. So electron hole pair generation will increase. Suppose here in the case only the holes are being considered. So here the initial concentration was p naught, and now after the turning on the light, it has reached the concentration p dash. Okay, but suppose at t is equals to 0, we have turned off the light, and then once we have turned on off the light, it is observed like whatever the excess electrons, excess holes have been generated, that are going to decrease exponentially, and at equilibrium it will finally, at a steady state, it will be reaching out to again the p naught value, p naught concentration of the holes only. Okay, so how this mathematics goes through, we will just analyze this. Okay, so here, so electron hole pair have been generated by putting the thermal energy, and once we have removed thermal energy, the electron hole pair recombination is going to take place such that the final concentration at equilibrium will be reaching out to the same value that was initially before applying the thermal energy. Okay, so that means what happens, on an average, whatever holes or electrons are there that are going to generate once we have applied thermal energy, and after removing the thermal energy, that electron or holes are again going to recombine with the available electron or available vacancies, so that it will be reaching out to the equilibrium state again. So the time, or the average time the electron or hole will exist, that is basically called a mean lifetime. So in case of uh, once electrons and holes have been generated and it has reached to a combination, so once it is generated and it has combined, so after the time between the generation and recombination is considered as the mean lifetime. So we can just write like on an average, a hole or an electron will exist for tau p or tau n seconds before recombination. So once an electron or hole have been generated by using this electron hole pair generation, so this electron and holes will be existing for an average time period, that is tau p for holes and tau n for electrons. So this tau n and tau p that exist such that before recombination, that amount of time it has been available into the crystal, so that tau p and tau n is considered as the carrier lifetime or mean lifetime, we call it. Okay, so this time is called mean lifetime. Okay, so we can just write tau p and tau n basically indicates, so this tau n and tau p basically indicates the time required, that indicates the time required for and electron holes and electron to return to their equilibrium concentration. That means basically this tau p and tau n is going to indicate what is the time required for electron and hole to return to their equilibrium. So initially the p naught was the concentration of holes, and after generation and then recombination it has again reached to p naught. So between t dash to reaching to p naught again, so at whatever level it is going to reach p naught, so this time will be considered as the average lifetime or the tau. Okay, for holes it is tau p, and for electrons it is tau n. Okay, so we will just relate the concentration of holes and electrons generated with respect to the concentration of uh, recombination of the concentration, the same holes and electrons. So suppose initially at equilibrium, the whole concentration is p naught and the electron concentration is n naught. Okay, so at t dash time, when the lights are turned on, the electron hole pair will start the generation of electron hole pair. Okay, so electron hole pair will be generated at this time. So at t equals to t dash, light is turned on, so this will result in electron hole pair generation. Okay, so electron hole pair have been generated. So whatever excess amount of concentration is there, that we will be considering here. So excess, or we can call it like injected concentration. In this case we can say like, so initially it was p naught, and after generation it has reached to p dash. Okay, so the excess amount will be p dash minus p naught will be the excess amount. Okay, so here the excess amount of concentration will be p dash minus p. This is for hole, and in similar case for electron it will be like n dash and not for electron. Okay, but whatever concentration of electrons or holes have been generated, the same equal amount of generation will be taking place. So whatever amount of electrons have been generated, the same amount of holes will be generated. So from there we can call it like p dash minus p naught will be equals to n naught minus n naught. Okay, so this is the amount of generation of holes, and this is the amount of generation of electrons. Okay, but one thing we can note here is like, so it was n type. we have taken n-type semiconductor. So n-type semiconductor is having like electrons and holes, but electrons are in much more quantity than holes in case of n-type semiconductor. Okay, so suppose 1000 electrons are there. For example, we have considered like 1000 electrons are there in n-type semiconductor, and holes are like 10 amount of holes are there, and after the generation of electron hole pair, suppose 100 electrons have been generated, and similarly 100 holes will be generated. So this is generated. Okay, so this amount have been generated. This is the initial amount. Okay, so if we consider the electron concentration overall, it is 1100 and this is 110. So if we consider the percentage increase, so percentage increase in case of holes and in case of electrons will be varying very much. So percentage increase will be very much in case of holes than the electrons, because electrons are already available in plenty amount of time, plenty amount of in quantity, but holes are very small in n-type semiconductor. So once the some amount of holes and electrons have been generated, so that hole concentration, that increase in hole concentration will be very much than the increase in electron concentration. Okay, so because of this, we will basically focusing on the you can say the property of minority carrier or the holes that have been increased by much amount of quantity. Okay, so we will basically focusing on the whole properties, like how it is going to behave. So one point that we need to mention here is like, once we are going to agitate n-type semiconductor with some thermal agitation that we have provided. So in n-type semiconductor, the thermal energy will not be increasing that amount of will not be increasing a sufficient amount of electron. That means that electron variation or the effect on the electron concentration will not be changing in a sufficient manner of time, manner of quantity. But in case of holes, that is minority carriers, once we are providing the thermal energy, this thermal energy will be increasing the minority carriers, and that will affect the quantity very high. Okay, the impact of the variation in the minority carriers will be very high. So this point we can note here, like the percentage increase in electron will be very small as n-type semiconductors are already has plenty of electrons, but in case of holes, there will be uh, a significant increase in hole concentration, or we can write like minority concentration. Okay, so this could be asked sometimes in objective type questions, like if p-type semiconductor is there and we have agitated it with the thermal energy, then what will be the increase in hole and electron concentration. Okay, so this point we can note from here. So that could be a part of like objective questions. The next point that we will be now seeing is how the, so our main discussion now will be based on the whole concentration only. Okay, so we are going to have the whole concentration effect, and how it is going to increase, like with time it is going to increase, and then it is going to decrease to reach to its equilibrium p naught value. So that's why in the figure also only the whole concentration is been mentioned. Okay, so here we can like note. So in other terms we can note like radiation radiation affects hardly to majority concentration. So whatever radiation we are providing, that will hardly affect the majority carrier. It will mainly affect the minority carriers. Okay, so that's why we need to, or in other points we can like radiation will affect mainly to minority concentration. Okay, so we will be focusing on the minority carriers only. Okay, so at steady state, that means at t equals to 0, the radiation has been removed. Okay, so but if we consider like the tau p, that is the carrier lifetime, is independent of, if tau p is independent of the whole concentration that has been generated, if this assumption have been made, if tau p is independent of the whole concentration, then the, you can say, a decrease in whole concentration per second due to recombination will be given like, so like we know initially it was p naught, now it has been p dash, and this p indicates the general value of holes. Okay, so now this p that is there, tau p is the carrier lifetime, like for what amount of time the generated holes will be existing before the recombination is going to take place. So the p divided by tau p, this will indicate the decrease in hole concentration per second due to recombination. Okay, so p was the total hole concentration, and it is going to decrease per second, so that will be like one hole is available for tau p time period. So in 1 second, p by tau p amount of holes will be disappearing or going for the recombination. Okay, that means this amount of holes will be decreasing per second. Okay, the next point, in case of generation, so basically we need to see like what is the amount of holes that have been generated and what is the amount of holes that have been uh, disappeared or used for recombination, and then by considering that amount we need to derive like why this whole concentration is going to increase, and then how this whole concentration that have reached to p dash is p bar is going to reduce to a p naught value again at equilibrium. Okay, so this is the amount of holes that have been decreasing, okay, per second due to recombination, and the amount that have been generated is given by like g. So this g is the amount of generated holes, so it will be like this amount of holes will in this will basically g amount of holes will increase the concentration, so increase in whole concentration, so g amount of whole concentration is going to increase per second due to thermal agitation. So suppose once we have applied thermal energy, g amount of holes are going to generate per second, then as we know, the by law of conservation of charge, or the like charge can neither be created nor be destroyed. So this g, if g is the amount of increase in hole concentration, and p by tau p is the decrease in hole concentration per second. Okay, so as we know, the law of conservation of charge says whatever increase in concentration per second is there, that we can depict from the value like rate of change of whole concentration per unit time, rate of change of uh, whole concentration per unit time, or this is like increase in whole concentration per second will be this, because in overall the whole concentration is going to increase. Okay, so whole concentration is going to increase, so whatever amount of because here initially p naught was the whole concentration, but it has increased from t dash to t naught, it has increased to p dash value. That means there is increase in whole concentration is going to take place. Okay, but p by tau p is the amount of decrease in whole concentration, and g is the amount of increase in whole concentration because of generation, and this is because of the recombination. But overall the concentration of holes are going to increase, so this increase per unit time dp by dt will be given as the, because it is going to increase, so increase in number of hole concentration because of thermal agitation minus this amount will be your rate of change of the holes per unit time. Okay, so this is like it will be equals to g minus p by tau p. This amount of hole concentration have been increased per unit time. Okay, that means at steady state, that means at t equals to 0, this rate is going to be 0. That means increase in the whole concentration is going to be 0 at t equals to 0, because we have removed as thermal agitation as or we can call it like light is turned off. So at t equals to t equals to 0, the light have been turned off, so there will not be an increase in whole concentration. So at that time the rate of change of whole concentration with respect to time will be 0. Okay, so if this is the case, then p, whatever the whole concentration is there, that will be reaching to p naught, that is at thermal equilibrium. Okay, so by this conditions, suppose this one is equation 1 and this is 2 and this is 3. 3 means as we are going to put the value t equals to 0, this is the condition, but at finally the whole concentration is going to reach to its thermal equilibrium p naught. So by putting this condition into the equation 1, we can get like the z value will be given by p naught divided by tau p. Okay, so now once we put all these conditions to a dp equation 1, we can get like dp by dt, rate of change of holes per unit time, is equals to p naught minus p divided by tau p. Okay, so now this is the rate of change of p, that is holes per unit time, but whatever excess amount of holes are there, that is excess amount of holes are basically given by the p dash. Okay, so here we can write like excess or injected uh, carrier concentration p dash is defined as the increase as the minority concentration above equilibrium okay, so p dash is the amount of increase, okay, into the equilibrium value, that is p naught. So p naught to p dash, it has increased. So overall we can see uh, this p dash value, that is the increase in the whole concentration, that is varying with respect to time. It is varying with respect to time. That means p dash will be a function of time. Okay, so we can put like the speed dash will be equivalent to whatever initial condition is there, whatever p value, that is holes are there at particular time, minus the initial condition. Okay, and it will be a function of time. So p dash is a function of time, and it is going to be represented like what at particular time, whatever the whole concentration is there, that is p minus the initial condition. Okay, so from there, if we find out the rate of change of the increased value, will be given like minus p dash divided by tau p. Okay, so this is the increase basically uh, in case of change in change in the whole concentration that have been changing with respect to time, and this change will be in showing a negative sign, because so this negative sign indicates that the change is a decrease in the basically here this change is basically decrease in case of the recombination, as in the recombination whatever this p dash uh, value is there, that is going to decrease. In case of generation, this p dash is like the positive value, that is whatever extra holes are going to generated. But in the recombination phase, this p dash value will be negative because it is going to decrease in recombination. Negative indicates uh, indicates decrease in whole concentration in recombination. So in recombination, this is going to decrease, and in when it is a generation, this value will be in positive. Okay, so at t less than or equal to 0, p dash 0 will be like whatever maximum value have been reached minus the p naught initial value. Okay, so this is the case if t is greater than or equal to 0. Okay, in that case the solution to this equation will be giving out the how the whole concentration is going to vary. So here it will like p dash T, its solution will be, if we solve this differential equation, it will be like P dash T will be the initial P dash value multiplied by e to the power minus T by tau P. Okay, so initial P dash value is nothing but the change, that is P dash minus P naught. So this has been increase in value at T naught up to T naught, and this is the initial value. So whatever increase in their value in the holes that is there, and this maximum value that is increased, that is P dash, is going to reduce with respect to the carrier lifetime. Okay, so this multiplied by e to the power T by tau P. Okay, and this will give you P minus P naught, because in this what particular time, at particular time, if the P is the value of the holes, minus P naught will be indicating this. So finally we can get like the P dash T, we can represent it like P dash minus P naught, whatever increase in hole concentration there, that is going to reduce with respect to time constant tau P naught. So this is the condition when T is greater than or equal to 0. So at T greater than or equal to 0, whatever excess amount of this was the excess amount of holes that have been generated is going to decrease. Okay, so the excess, this is the excess amount of holes generated. So this excess amount of holes is basically going to exponentially decrease, and this exponential decrease will be such that it is going to be decreased to a zero value. Okay, this decrease will be such that it will be going to decrease and it will reach to P naught value. Okay, basically, or we can say like the excess amount is going to decrease to zero. So excess amount is going to decrease to zero means P dash minus P naught is going to decrease to a zero. So its value like P dash value will be equal to zero, or we can call it P value will be equals to P naught. So finally it will reaching to the P naught value, that is the value at equilibrium that was before the application of the light or the thermal energy. Okay, so we can just write like the excess concentration decreases exponentially to zero. That means the excess concentration is going to decrease to zero. That means P dash is going to decrease to zero, or we can call it like P is going to reach to P naught. Okay, with time constant equal to mean lifetime, that is tau P. Okay, so this is how the generation of charge carriers and a recombination of charge carriers in a particular semiconductor is going to take place. So this is the case of n-type semiconductor. Okay, so in n-type semiconductor, minority carriers will be basically the holes, and holes uh, will only be a significant change. Hole concentration will only be a significant change in the once we have applied the light or thermal agitation. So similarly, in case of p-type, if we go with the analysis, in p-type the minority carriers will be electrons. So electrons will be only having the change that will be a significant to the change in the electron concentration, so that will only be going to be analyzed. Okay, and whole concentration will not be of that much amount of quantity, then it is already available in the p-type semiconductor. So that analysis will be uh, not be done. Okay, so the next point uh, we need to see is, as we are going to have like thermal agitation, some electrons are going to generate, and holes are going to generate, basically electron and hole pair will be generating. So there is like whatever, sometimes what happens, if in the recombination phase, like if we are going to increase the thermal agitation, the electrons from the conduction band uh, will be going to combine with the holes available in the valence band. So in that case there will be a transition of, you can say, the electrons from conduction band to valence band. So basically based on this transition of electrons from the conduction band to valence band, there is a classification of a semiconductor based on this movement of electrons from the conduction band to valence band. So that classification is basically, semiconductor is there, it is classified as a direct band gap semiconductor, and one is called indirect band gap of semiconductor. Indirect band gap semiconductors. Okay, so we will see like how this direct band gap and indirect band gap semiconductors uh, are there, and what are the examples of these semiconductors, and how its properties are going to vary with respect to direct and indirect band gap semiconductors. Okay, so we will see some points: direct band gap and indirect band gap semiconductors. Basically this is going to take place in the case of recombination. So in recombination, basically this process, recombination is the process where electron moves from conduction band into the valence band, so that a mobile electron hole pair is going to disappear. Okay, so this, and some, once it is moving from the conduction band to valence band, sometimes it moves to directly from the valence band to conduction band, or sometimes it is going to collide. Okay, so suppose this is the conduction band and it is valence band, so some electrons are available here. So while a recombination is going to take place, this electron will move to here. Okay, so once it is moving from direct conduction band to valence band directly, so it will be a direct band gap semiconductor. Sometimes this electron moves to valence band, but with some hoping, like it will be reaching to a particular level, it will first reach to here, and then again from here it will be moving to the valence band. So these type of semiconductors are called indirect band gap. So these are indirect band gap and these are direct band gap semiconductors. It is directly moving the electrons from conduction band to valence band, it is direct. If it is moving from conduction band to valence band, but between some intermediate energy levels, it is reaching to a particular energy level and then it is moving to valence band, these are called indirect band gap semiconductors. This is like how we can visualize the uh, direct and indirect band gap semiconductors. So we will see some points. Okay, so what is basically, so in direct band gap semiconductors, basically during the recombination most of the energy dissipate here in the form of light. So if any semiconductor is there, the electron is moving from conduction band to valence band directly without any hopping. Okay, then it will be, because it is moving the electron from valence conduction band to valence band, it will be reducing, or it is going to dissipate the energy. So that dissipation of energy basically will be in terms of light. Okay, so here the, in terms of light, this energy will be dissipated. Here in indirect band gap semiconductors, this energy dissipation will be in terms of heat. Okay, so whatever semiconductors are there, so LEDs that we see, LEDs are made up of LEDs, light emitting diode. Okay, it is a semiconductor device. So LEDs, in LEDs basically recombination takes place from com, uh, conduction band to valence band, so it is a direct band gap semiconductor. So all the LEDs will be a direct band gap semiconductors, because once it is electrons are moving from conduction band to valence band, it is going to give light. The energy is going to be dissipated in terms of light by giving the light. But if indirect band gap semiconductor is there, we cannot use that indirect band gap semiconductors for designing an LED, because in indirect it is there is an intermediate level. So there the energy will be dissipated from moving to conduction band to intermediate level and intermediate level to valence band. So there will be a dissipation of energy in terms of heat. So it is not going to work as a LED, because it will be dissipation the energy in terms of heat. Okay, so here in a recombination, basically the energy is dissipated energy dissipation will be in terms of the light. Okay, so that's why it can be used as the LEDs. So the example of this direct band gap semiconductors are gallium arsenide or gallium nitride, indium arsenide. Okay, so there are many examples of this direct band gap semiconductors are there. So in terms of indirect band gap semiconductors, we can note like here the recombination will be such that uh, the energy dissipation will be in terms of heat. Okay, so the example of the indirect band gap semiconductors are like silicon and germanium and aluminum phosphide, aluminum arsenide. Okay, so these are the some of the examples, like a gallium phosphide. Okay, so these are indirect band gap semiconductors. So other point that we can see here is like during a recombination in direct band gap semiconductors, most of the free electrons will be directly falling from the conduction band to a valence band. So here this is like conduction band, this is valence band. So in case of direct band gap semiconductors, most of the electrons will be moving to conduction band to valence band, and some may be colliding with each other. So collision will be taking place in some of the cases, but mostly like 90% will be uh, moving directly, and around 1% or less than 1% is going to collide. 99% will be directly moving and 1% will be colliding. So this is the case in case of uh, direct band gap. So here once it is directly moving, it will be generating the light. So 90% of electrons movement will be generating the light, and this collision will be dissipating in terms of heat. So that is collision, this heat dissipation will only be taking in 1% chance, and in 99% chances the light will be generated by dissipating the energy. Okay, in terms of direct band gap semiconductor. But in case of indirect band gap, during the recombination, most of the free electrons are falling from conduction band to the valence band, will be going with the intermediate level. Okay, so here it will be like so there is an intermediate level. This is conduction band, valence band. So 99% will be going with the collision, and 1% will be in direct transition. Okay, direct band gap transition from conduction band to valence band, but 99% will be colliding. So most of the colliding electrons are going to dissipate the heat. Okay, so these are some of the points that we should be considering in case of the direct band gap and indirect band gap semiconductors, and the examples. So their examples are also we need to consider. Okay, so some examples that we have seen. So there are different type of direct and indirect band gap semiconductors. So some objective type questions in even gate have been asked in through this, and in some competitive exams you will be getting this. Okay, and so I think the time is over now. So the next topic we will cover into the next class. So this we will stop now.